Hi everybody, my name is Maristany and I'm a physics PhD student at Robinson College in the University of Cambridge. I was born and raised in Argentina, a country in the southernmost part of South America. I did my bachelor there, but I decided to move to Canada to pursue a Master's of Theoretical Physics at the Perimeter Institute in the University of Waterloo. Finally, in October of 2020, I moved to England at Cambridge so that I could start my PhD in Theoretical Biophysics.
Today, I want to talk to you about one of the most exciting paradoxes of modern physics. So, let's jump in. To begin, we need to remind ourselves about what black holes actually are. Maybe you have heard of something called the fabric of space-time. Our reality is embedded in time and space coordinates in something that we ultimately call the space-time continuum. Massive objects such as stars or planets bend space-time, creating gravitational forces around them. A black hole is an object so massive that the curvature it causes on space-time is infinite. We call that a singularity. A singularity is the region of space-time where the gravitational forces become infinite. But what exactly does this mean? Well, let's imagine that we're standing in the surface of Earth and then we're bouncing a ball. The ball will bounce back, and this is due to the force of gravity. Let's say that we bounce it stronger, and the ball, of course, will bounce up higher. If we do it even stronger, there is a possibility that, at some point, the ball will escape Earth. Gravity being infinite in a singularity means that if you're standing in a black hole, no matter how strongly you bounce the ball, it can never ever escape. As a matter of fact, nothing can escape a black hole. If you light a lantern on the heart of a black hole, the light of the lantern will never escape the black hole, always turning back into itself. Perhaps another way of understanding how a black hole works is to equate it to a tub full of water. When you pull the plug, the water starts swirling around it and starts escaping it faster and faster. This is very similar to what happens with matter around a black hole. The effects of the infinite gravitational forces of the singularity causes matter to swirl around the black hole, and anything that is closer to what we call the event horizon will fall inside of it. This is even more apparent if we remember that in the center of every galaxy there is a black hole. A fun thought experiment that usually helps us understand a little bit how a black hole behaves is to ask ourselves what would happen if the sun in our solar system suddenly became a black hole. Gravitational fields only depend on the mass of the object. So, if our sun suddenly were to become a black hole of the same mass as originally our sun has, then nothing would actually happen, since the gravitational field around the solar system will remain to be the same. The event horizon and the Schwarzschild radius also depend on the mass of the black hole, and in the case of our sun, if it were to become a black hole, the event horizon and the Schwarzschild radius would be too small to swallow any of the planets that are gravitating around it. So let's recapitulate a little bit. A black hole then consists of a singularity, a region of infinite gravity. The singularity is surrounded by something that we call the event horizon, which is the region around the black hole of which the gravity is so strong that you cannot escape it anymore. The size of the event horizon is called the Schwarzschild radius. To illustrate better what an event horizon means, let's see what happens when a shooting star comes close to a black hole. If the shooting star avoids the event horizon, its path may be deviated, but it will not fall into the black hole. Whereas, if the shooting star falls inside of the event horizon, then it can never escape the black hole again. Now, physics is an incredibly wide and rich field, comprising of many subfields. The paradox that I want to talk to you about today lies in the interface of two of the most famous theories in physics of the 20th century, that of general relativity and of quantum mechanics. It is called the black hole information loss paradox. Now, as with many other areas of physics, there are laws within quantum mechanics. You're probably already familiar with other laws of physics, such as Newton's laws of motion. One of the main and most important laws within quantum mechanics is that information cannot be created nor destroyed. This may sound a bit weird, since you might ask yourself, okay, but what happens when I just grab a piece of paper and I just burn it to the ground? In that case, you may argue that the information that the piece of paper contained has been completely destroyed. However, if you know exactly how the piece of paper was burned, you can possibly reconstruct it piece by piece and regain again the original information. The information that we're talking about in here is not just the information that you can find written in a piece of paper. We're also talking about quantum information, which is the information that is encoded within the elementary particles that make up all the matter and energy around us. So, how does this relate to black holes? Well, let's say that I grab this law, I write it in a piece of paper, and I throw it inside of a black hole. As I have said before, nothing can escape a black hole. So there is actually no way for me to be able to recover the information that I just threw inside of it. This is not necessarily a paradox in itself, since we may argue that, okay, we cannot access the information, but the information is still there, in the heart of the black hole.
To understand the paradoxical aspects of information being absorbed into a black hole, we need to go back to quantum theory and talk about one of the main discoveries of one of the most famous physicists of the 20th century, here in Cambridge, Professor Stephen Hawking. But let's rewind and start very slowly. I am sure you have heard that most of the universe and the outer space is just filled with vacuum. But, contrary to what we learned, when we consider quantum theory, we discover that vacuum is not real vacuum. It is not static. Instead, there is a phenomenon called quantum fluctuations or vacuum fluctuations. In very simple terms, vacuum fluctuations refer to the spontaneous creation of a particle and an antiparticle in a point in space. Because they're created spontaneously next to each other, they're almost always immediately annihilated. This is why, to the naked eye and without any incredibly precise instrument of measurement, vacuums appears as just that, vacuum, static and empty. These teeny tiny vacuum fluctuations, however, play a major role when they occur very close to the event horizon of a black hole. Sometimes, when the creation of these pairs of particles occur near the event horizon of a black hole, one of these particles would be absorbed by the black hole, while the other one is emitted to the outside world. This phenomenon is known as Hawking radiation. Hawking radiation causes the black hole to lose small amounts of energy every time that a particle escapes, and therefore to lose a small portion of its mass over time. This is because energy and mass are related. Let's remember Einstein's famous equation E equals mc squared. Over time, Hawking radiation causes black holes to shrink, and ultimately, after millions and millions of years pass, the black hole will completely vanish. Well, this poses a little bit of a problem, because now we really do not know what happened to all of the information that we have previously thrown inside of the black hole. This is the paradox. As it stands, general relativity and quantum theory seem to be irreconcilable, since black holes seem to be breaking one of the fundamental laws of quantum mechanics, that information cannot be destroyed. This paradox has puzzled physicists for many years. A lot of them have come up with many different solutions to the problem. One possible, perhaps straightforward solution is to say, okay, information is lost forever. As you can imagine, the main problem with this solution is that it violates one of the core principles of quantum mechanics. And to be fair, quantum mechanics is not a theory that we're quite so ready to get rid of yet. This is mostly because quantum mechanics has proven to be an incredibly accurate theory, and it has allowed us to make incredible advances in our understanding of our reality. Another proposed solution was to think that the information suddenly escaped the black hole in the last possible fraction of a second on which the black hole finalizes evaporating. This solution is a particularly appealing one, since it not only explains the paradox,
but it does so in a way that it allows us to continue having the same models in physics without fundamentally changing them. This is because the moment on which our models would break is contained to a very specific moment in time, while still being valid for the rest of the process of the black hole evaporation. But, of course, as you may have guessed, there is still a problem with this proposed solution. Just before the black hole evaporates, when the black hole is very, very tiny, this solution implies that it should be able to store an incredibly large amount of information. This violates something called the Bekenstein bound, which is a limit on the amount of information that can be stored in a particular region in space. Another possibility is that after the black hole is evaporated, information is stored in a remnant, either an incredibly tiny one called a Planck-size remnant, or a bigger one. The remnant proposal still has significant challenges. A lot of work has been published outlining constraints on those possible hypothetical remnants. The main challenge that they face is called the infinite production problem. This problem might be a little bit too technical, but let's see if I can summarize it in a few words. The problem is that if you do the math, and if you apply something called effective field theory, then you end up with a very curious realization. This is that if you accept that such a thing as a remnant exists, then the actual vacuum would be unstable and it would produce an infinite amount of remnants. And this is something that we quite obviously do not observe in nature. Many physicists have worked and are working in this problem and have proposed different solutions or loopholes to going around it. But as you can see, this is also not a straightforward solution to the paradox. We still have another proposed solution that seems straight out of a science fiction movie. This solution proposes the existence of something called baby universes. It states that information is actually stored in a baby universe which is separated from our own universe. We can think of a baby universe as a universe that sort of branched out the main one. The problem with this theory is that it's just incredibly hard to test. And it is very hard in physics to say that a theory is correct if we cannot accurately test it on a laboratory. Finally, one of the perhaps most accepted solutions to the paradox is the idea that information actually gradually leaves the black hole as the black hole is evaporating. This proposed solution basically thinks that Hawking radiation has enough time to learn the information that the black hole is storing before going off to the outside world. This implies that information stored in the black hole is actually stored not in its heart, but in its boundary. It is related to something called the holographic principle, which states that the information stored in a black hole is not in the bulk of the black hole, but in the two-dimensional surface that surrounds it. You may have heard before the very overly simplified phrase, the universe is actually a hologram. Well, this comes actually from the idea of the holographic principle. The theory that our current universe is a hologram is actually the theory that the information that we can access is embedded in the surface of a larger dimensional object. But let's go back to the original paradox. As you can see, solving it has been no easy endeavor. In the efforts of doing so, however, a great deal of advances have been made in general relativity, ADS-CFT theory, and quantum information science. The paradox seems to have been at least partially solved by a team of scientists in 2019, 45 years after the discovery of Hawking radiation. The solution involved a plethora of calculation, the inclusion of wormholes, and also elements of a relatively new field called quantum gravity. This is, however, not the end. There are still a lot of things that we do not understand when it comes to information and black holes. I really hope you have enjoyed this lecture. Right at the end here, I'm going to show a list of resources and the bibliography that I've used to put together this video. They're all very accessible, and if you're interested in the topic, I will strongly recommend that you check them out. Until next time!